Talk to you about memory and AI models. And so it is my hypothesis that memory is going to come up more and more as a subject around models as opposed to like scaling up. Like trying to make bigger and bigger models. We'll focus more on making models that can remember information, remember more information, and remember information for longer periods of time, and access that memory better than other models. And then so there's a lot of, like thought that goes into that, and a lot of different competing frameworks overall. But I can give you my 2 cents overall on this subject and my opinions. And then so up front, this is my opinions as to the best framework here, right? I could be completely wrong with my upfront assumption with this, flat out, and I'll give you my upfront assumption. My upfront assumption is that memory very specifically needs a probabilistic aspect in order for it to like actually function properly. I think that you can't just encode memories into like a graph system because it's too linear, where it's just you have like 100% perfect recall. I think that when I look towards and I think about human memory, it's lossy, and that's across the board, right? That's one thing that we can 100% agree on. Every human on the planet is that memory is lossy. And then so I think with that, I turn it like, okay, if it's 100%, if this is something that is inherent within 100% of people, and so as far as we know, it's inherent within 100% of like biological memory, then perhaps it is actually a feature and not a bug. And so within that, I think about that more and more. And then so I think about structures that very specifically mimic human memory as opposed to other structures. So like graph structures, other structures, I throw them out in this instance very flat out. So in my opinion on this, we're talking about hyperdimensional computing when it comes to memory. And then up front, I tread very carefully when it comes to HDC and hyperdimensional computing, because I do have competing interests in this category. But I think this is far enough away and far enough removed from those, and this is just a high level enough with regards towards HDC that this is okay with this video. So overall, this notebook purpose is to demonstrate two particular systems that I think are the most advanced when it comes to memory retrieval systems. And these aren't systems that I created. They're vector symbolic architectures, or VSA, and sparse distributed memory, or SDM. This notebook demonstrates two related concepts in the fields of HDC. And so sparse distributed memory, or SDM, is a specific model of associative memory inspired by the structure of the human brain very specifically. It uses high dimensional vectors and Hamming distance to store and retrieve information, whereas vector symbolic architecture, or VSA, is a more general framework for representing and manipulating information using high-dimensional vectors. It defines core operations like binding and superposition that allow for the creation of complex representations from simpler ones. Essentially, SDM is like what is the best representation if we're mapping it 100% kind of like biologically, and then VSA is what if we took out everything that we know and we built it from like the ground up from scratch, right? And then so first one we'll look at here is SDM utilizing Hamming distance, as we can see here, and then so it utilizes Hamming distance to write the vectors specifically to memory. And then I have down here a further explanation of both of these architectures. I won't go into both of them here very specifically, but like in depth. But so SDM is a computational model of associative memory inspired by the distributed nature of information storage in the human brain. It's a type of neural network, but it differs significantly from typical deep learning models. Essentially, a breakdown of it is it utilizes high-dimensional space, and then so high-dimensional space is essentially like where you're talking about lots of vectors, right? 1,000 plus vectors, and then each vector is an individual dimension. A lot of this deals with dimensionality. A lot of my videos deal with dimensionality, right? Dimensionality is just a concept, a mathematical concept related to vectors in this instance. And then each individual vector can represent one individual dimension. And then so each dimension could be thought of as an individual feature, although features themselves are not explicitly defined, right? Like there's That's the bottom line of all of this, and it's an important concept within this, right? Like, what is signal and noise is human defined within this. We define it ourselves. So 2 is binary vectors. Both addresses and locations in memory and data are represented as binary vectors. Each element of the vector is either a +1 or a -1. Sometimes 0 and 1 are used, but +1 and -1 is most common. And then you have an address space and hard locations, which represent neurons, your distributed storage, so you can get your probabilistic aspects into there, associated retrieval, your handling distance calculations, your access radius, adding some sort of probability into there, and then essentially you just mix that all together. So in simple terms, the idea is that you imagine a vast library, the address space, which only a few actual bookshelves, like hard locations. With each book is the data, and each shelf is the hard location, has a very long, unique barcode or a binary vector. So when writing to a book, you scan its barcode. You then find the shelves with the most similar barcodes using handling distance, and you place a copy of the book on each of those shelves. This distributes the information. To retrieve a book, you provide a barcode, a query vector, and then you find the shelves with the most similar barcodes. You then look at all of the books on the shelves and combine them using a weighted average effectively to reconstruct the original book. Because information is distributed, even if some shelves are damaged or the query is slightly wrong, you can still retrieve a good approximation of the original book. Advantages of SDM overall are its robustness, associativeness, capacity, and generalization. It is very computationally costly to run. It will take you a long time to run this. Inference costs can be massive, and it's not a perfect model of human memory. While it's inspired by the brain, it's still a simplification. And then diving into VSA, on the other hand, so vector symbolic architecture, it's essentially, again, playing off of dimensionality, right? So VSA, also known as hyperdimensional computing, is a computational framework for representing and manipulating information using high-dimensional vectors or hypervectors. Unlike traditional symbolic AI, which uses discrete symbols, VSA uses distributed representations. It's particularly well suited for tasks involving analogy, similarity, and cognitive modeling. The core concepts are hypervectors themselves, randomness, and near orthogonality. And so this is crucial. If you generate 2 random hypervectors, they'll almost certainly have a very small dot product, close to 0, indicating near orthogonality. This allows us to represent the distinct concepts within dissimilar vectors. Binding. So binding, unbinding, and superposition are like the main ways that the models do this, right? So binding is an operation that combines 2 hypervectors to create a new vector that is dissimilar to both of its inputs. A plus B doesn't equal C. A plus B equals Z. This are 1. This is used to represent relationships or associations between concepts. The code uses element-wise multiplication as the binding operation, and this is a common and effective choice for bipolar vectors. The resulting vector is also bipolar. Within superposition, an operation that combines multiple hypervectors to create a new hypervector that is similar to all of its inputs. So the reverse of binding, right? This is in that instance. This is used to represent sets, combinations, or bundles of concepts. Binding and bundling. Binding and bundling. The code uses element-wise addition followed by normalization, taking the sign, and this is a common method, and the resulting vector is also bipolar. So you have the concept of binding and bundling. You can also unbind, right? And then so it's the approximate inverse of binding, and then you can also find similarity based off of this, which is the measure of how alike 2 hypervectors are. And then essentially that's the overall gist. So in simple terms, imagine you have a very special high-tech dice, which are hypervectors. Each die, it's a thousand face die, right? And each face shows either +1 or -1. And then so it's a random dice. If you roll 2 different dice, the pattern of +1s and -1s will almost be completely different, near orthogonal. To represent dog chases, you would take the dog die and the chases die and create a new die by multiplying the corresponding faces together. So you would do bundling and binding, right? Bundling and binding. So +1 times +1 equals +1 +1. x minus 1 equals minus 1, etc. And then this new dog chases, like the new dice, will look very different from both the dog and the chases dice. The event, and then you get into superposition and cleanup within this. The advantages of VSA are that it's robust to noise, it provides distributed representations, it provides fast operations, it's a cognitive modeling system, and it's one shot. You just do it and that's it, right? That's both an advantage and a disadvantage to the system. Limitations: scalability of retrieval. The retrieve memory function in the provided code iterates through all stored vectors. So for very large memories, this can become slow. Again, both these memories both of these methods are very compute intensive. Representational power. While VSA is good at representing relationships and sets, it's not as expressive as some other symbolic AI approaches. It's also not the most interpretable. It can be hard to directly interpret the meaning encoded within a given hypervector when you're just, 1,000 dimensions. It's not very human interpretable overall. But so bottom line, if you're into memory, which I think I've seen a lot more focus on, which is why I'm creating this video here, this gives you good introduction into two methods that you should be looking at overall that are probabilistic based, right? So in my opinion, probabilistic memory as opposed to linear is much better. And then so these are very focused on that. If you like this type of content, please like and subscribe. Thank you very much.